Hello, my lovely students. Now we get to talk about logs and how much I hate the way the book and most books present them. So, logs were designed, their whole purpose in life is to undo exponential functions. So, a lot of books present it as, oh, well, these things move here and this moves here, and look, it's the same as an exponential, just written in a different way. That's great, unless you're dyslexic or you get the order wrong. Like I did see some of the videos online where it was like this around and in. I was like, okay, B to the A equals C. Okay, I can get behind that a little, but I prefer you understand that logs do a thing the same way square roots do a thing and trig functions do a thing. All right, so I have this lovely definition here. The base actually inherits the same restrictions from exponentials, has to be positive, can't be 1. Logarithms, though, because exponentials, normal exponentials are only positive numbers, logarithms have a restricted domain. Their domain can only be from 0 to infinity unless you shift it around. So that's me babbling about what I was just saying. Logs are things, processes you do. Okay. So we get a whole bunch of little practices. Log base 6 of the square root of 6 equals 1/2. This is wanting us to write in exponential form. So the way I write takes longer, but I find has more meaning because you get used to seeing the log or the exponential do the thing they can do. All right, so log base 6 of this square root of 6 equals 1/2. So log base 6 is the inverse of 6 to the x, which I call it the 6 exponential or 6 to the. So what I'm going to do is I'm going to take these two things that are equal and use one of the properties of exponentials, which if I have two equal things, then if I take the same base raised to those exponents, they are also equal. So this is another do the same thing to both sides. It's just what we're doing it with is a little weird. But what we're doing it with is the inverse function of the thing we see that we want to not see anymore. So 6 to the log base 6 both cancel, and we are left with the square root of 6 equals 6 to the 1/2, which is true. The square root is the same as the 1/2 power because it's the power that cancels out squaring. 2 times a half is 1. All right. Same song, second verse, B. Log base 3 of 9 equals 2. So canceling out log base 3 with 3 to the on both sides. So we end up with 9 is 3 squared. Now, if you're comfortable doing the whole label what each part is, label where they go, that's fine. Or the whole like loop-de-loop arrow thing, that's fine. But there comes a time in calculus where you have to understand that there's times when you have a giant product and you're being asked to take the derivative of it, and it is multiple product, it's ugly. But if you take the log of it, then it's a bunch of sums. It's a lot nicer. But to undo taking the log, at the end, you end up taking the exponential of both sides to undo that log you took earlier. Now, this also works because e to the x and ln of x are both strictly increasing functions. They never wiggle back around. So if I take the ln of both sides, or if I take e to the of both sides of an equation, It's going to preserve which one is bigger or which one is smaller, the direction of growth, all of that. So that's why these functions are so nice, and they actually get exploited royally in a good way in statistics. If you don't see a pattern, take the log of it, see if something happens. If not, take the exponential, see if something happens. Because it will cluster numbers that are closer together than other numbers. So if the data looks too random, like taking the log of it can actually make the points cluster in a more obvious pattern. All right, so now we have log, again, going to exponential. So log base 10 of 1,000,000 equals 6. So canceling out log base 10 with 10 to the, so we get 1,000,000 is 10 to the 6th. Log base 5 of 25, 5 to the 25 equals 5 squared. I just put a whole lot of these here for practice. Now we're going the other way around. We have exponential equations. We're going to write them in logarithmic form. This is where logs are very powerful, because imagine instead of 2 to the 3rd, it was 2 to the x. Now, if it equals 8, yeah, we can figure out x is 3. But if it equaled 9, I don't know what x is then. I know it'll be a little bit bigger than 3, but is it 3.1? Is it 3.2? Is it 3.01? I don't know. This is the power of logs. So 2 to the 3rd equals 8. So I am going to apply log base 2 to both sides. Log base 2 of 2 to the is the same as 2 to the log base 2 of. They undo each other. So on this left side, all we have is the 3. And on the right side, we have log base 2 of 8. You might have to type the equation the other way around. Log base 2 of 8 equals 3. If we even have questions that make you do this. But to me, it's less like, look at the numbers dance and move. Now you do the dance. No. So this is 5 squared. 5 is the base. So log base 5. Log base 5. 2 equals log base 5 of 25. Now the same way when we square root both sides, it has to be the entire side. Same thing when we apply it to equations. It's applied to each entire side. Therein lies its power. So 10 to the negative 4th equals 1 over 10,000. All right, so 10 is one of our special numbers with logs. 10 is the base of our counting system because most people have 10 fingers. So instead of writing log base 10, which we still can do, it was just decided by mathematicians that's going to be common log. So if I don't write a number, assume it's base 10, because a lot of the times we use base 10. So we want to take the log of both sides. I'm going to go ahead and write the 10 just to be consistent, but I'll write a little note to the side as well. So this is negative 4 equals log base 10 of 1 over 10,000. But this could also just be written as log of 1 over 10,000. All right, more. So if I have 3 squared equals 9. Then I take log base 3 of both sides. I get 2 equals log base 3 of 9. Five to the third is 125. So I apply log base 5 to both sides. 3 equals log base 5 of 125. And then our last one, we get a negative number showing up. But it's a negative exponent. That's okay. So I would apply log base 2 to both sides. So this becomes -1 equals log base 2 of 1/2. So I didn't log a negative number. I did a log that involved a negative exponent. That is okay. A log can equal a negative, but we cannot apply a log to a negative. So that is like one of the catches when you log a function, is it doesn't technically work on the negative side of things. But we spend most of calculus being like, focus on the positive, ignore the negatives. Because it's what you do in most real world situations. All right. So logs actually are asking a question. They're asking what power does the thing? So when we say log base 7 of 49, that is asking 7 to what power is 49? Or log base 3 of 27 is asking 3 to what unknown power is 27? So when we see these other ones down here, log base 4 of 64, this is asking 4 to what power is 64? Well, 64, if we divide it by 4, we get 16. So 64 is 4 times 4 times 4. Yes, thank you, 64 equals 64. Which is 4 to the third. So 4 to what power? The third power. Meaning y equals 3 there. Over here, this is asking, and don't think it has to be like, oh, the bigger number has to be the inside the log, the smaller number has to be the base. It doesn't. This is asking 121 to what power equals 11? Well, I know that the square root of 121 is 11. And I know the square root is the same as the 1/2 power. So this means log base 121 of 11 equals 1/2. There are ways to type this on the calculator. It involves using a formula called the change of base formula. So I'm going to go ahead and write that here. So log base b of a for any b can also be calculated using log of a divided by log of b, which this is common log, so it's log base 10. This also equals the natural log. Notice I write a capital L, it's not an I. The natural log of A over the natural log of B. So many people wrote IN. It was driving me bonkers last semester. Please don't write an I. It's an L. I know when you look at it typed, it looks like IN, but it's not. So if I wanted to know what this log equaled using the calculator, I would do the log of 11 over the log of 121, make sure my parenthesis closes after the 11, and it would tell me 0.5, which we know is 1/2. Ooh, now we have logs of reciprocals. Oh no! All right. So another way to look at this is to mess around with the number inside. So 27 is 3 times 9. 9 is 3 times 3. So 27 is 3 to the third. So this is really log base 3 of 1 over 3 to the third. So another way to rewrite that nonsense inside is using our negative exponent rules. This guy is in the basement. If I decide to move him, he is not going to be happy with me. He's going to say, I didn't want to live up here. I work night shifts. It's too bright. I hate it. Negative power. But now I have my log base 3, 3 to the, they cancel. So this equals -3. This is why I like my log exponential interactions. I'm not having to remember that question. I'm just having to remember, what does a log do? A log messes up an exponential, undoes exponentials. So same thing over here, log base 2, 1 over 32. 32 is a power of 2. That is actually 2 multiplied 5 times. So this is a log base 2 of 2 to the -5. Log base 2 of 2 to the, all cancels out, and this equals -5. So totally fine for a log to equal a negative. All right, there's the end of that video.